Alright, so now that we've taken a look at how the electron configuration relates to the periodic table, we can then say that there's a correlation between kind of the electron configuration and elemental properties as a result. So let's take a look at some of these real quick. When we take a look at the periodic table, we'll see that it's kind of divvied up into three regions, for lack of a better word. We've got a periodic table that looks something like this. We talked about how we have our S block, P block, and D block. But when we take a look at some elements in the middle, particularly things like boron, silicon, and kind of working our way down and over, there's this green staircase in the middle here. So this is things like boron, silicon. We've got, not so much this one, germanium, arsenic, antimony, tellurium, and working our way down. Anything in this staircase-like region is going to be one of the pieces that divides the periodic table. And we'll come back to this here in just a minute with the fact that this is called the metalloids. And that's because these are hybrids of elements on either side. And when I say hybrids, it means they have properties like the elements on the left side of the staircase and properties of the elements on the right side of the staircase. So anything in this region over here that I'm drawing in with these blue lines are called nonmetals. And these nonmetals are considered to be elements that gain valence electrons in chemical reactions. We'll also see that a lot of these nonmetals are often kind of very dull to look at. They're not very shiny. They're often very brittle substances if they're solids. But we'll normally see that they also exist as liquids and gases. And this region that I'm going to shade in orange that's pretty much a lot of the elements on the periodic table on the left side. This orange region, we call these elements metals. And that's because they're very shiny. Let's see, what else about metals? We normally see that they're also going to be pretty hard. And they're going to be pretty hard and solid, and they can kind of like take a little bit of abuse versus the brittle solids of our nonmetals. We'll also see that these elements lose valence electrons in chemical reactions. And we'll see that the reason for this has a lot to do with the way the atoms are structured. So if you'll recall, we talked about this idea of shielding and penetration of electrons and the nucleus, right? So if you'll recall, we talked about how if we have the nucleus here that has like a +3 charge on it, we have this n equals 1 level in the 1s orbital with our 2 electrons there. And then we went out one more, and we had 1 electron out here. We talked about the idea of shielding, whereas these two electrons, the 2 core electrons, I'm going to use the word feel very loosely, feel a pull of +3, whereas this one electron has two minuses canceling out the three pluses. And so it feels a pull of +1 on that valence electron there. So because of this, and the kind of what the overall pull is, we'll sometimes see electrons are attracted to an atom, or we'll see that atoms are repelled. And the metalloids in the middle, well, they're kind of a hybrid. Sometimes they lose valence electrons, sometimes they gain valence electrons in chemical reactions. It depends on what we pair with them. We'll also see that metals will conduct electricity, so we call them conductors, whereas our nonmetals are considered insulators because they don't conduct heat and electricity well. Metalloids, on the other hand, are somewhere in the middle, and they're a class of compounds that are called semiconductors. And we'll see that these semiconductors have a really important role in society. This is what allows us to have things like touchscreens. And a lot of that is because of the indium that is inside of the indium and the germanium that are mainly inside of your touchscreen glass surfaces. So, a couple other key important things have to do with naming some of the main group elements. When we take a look at what the periodic table looks like, I'm going to mainly look at the main groups here. This is the transitions in the middle. So, in this case, when we take a look at the periodic table, we'll see that each column, or each family, or each group has its own unique name. And that's because each column, family, or group in this main group set behaves very similarly. So, for example, if I'm in this first family here, this is often called the alkali metals. And that's because when they're added to water, they turn water basic. And so they make it alkaline. We'll see the second column is called the alkaline earth metals. And that's because these are metals that do the same thing, but you can find them in the Earth's crust. We'll see that this sixth column over here is called the chalcogens. We'll see the seventh column is called the halogens. And the eighth group is called the noble gases. Now, when we take a look at these periodic tables and these group names, there are names for the other ones. For the other groups, but they're so outdated that nobody really uses them anymore. So instead of calling them by a special name, you can also see that they're named by the element at the top of the periodic table. So in this case, instead of calling this the seventh group the halogens, I could also call it the fluorine family. And that's because fluorine is the element that's at the top of that column. So you may hear certain groups named according to what their position is in the periodic table. So a few other important pieces are going to be additional characteristics that we see in common with these main group elements. So these main group elements are, again, the S and P blocks. And we'll see that these all have the same characteristics in common. When we take a look at the number of valence electrons, I'm going to draw these out in like a green color. We'll see that there's 1 in the lithium family, 2 in beryllium, 3 in boron, 4 in carbon, working all the way across to have our different number of valence electrons. We'll also observe that we're able to predictably identify the common charges on most of these main group elements. And I'm going to list these charges out in orange at the bottom. So in this case, in the alkali earth metal, we'll see that there's 1 valence electron to lose, so it becomes a plus charge, and that we indicate just as a regular plus sign to indicate there's 1 plus. However, in the alkaline earth metals, we'll see that this is a 2 plus, 3 plus, 4 minus, 3 minus, 2 minus, 1 minus, and 0. We'll see that the group on the end, the noble gases, very rarely react with anything. In fact, it's really only xenon of the noble gases that'll even react with other elements. And that's because of a special exception with fluorine. And the reason that these very rarely react is because they have a full energy level. However, when we take a look at our halogens, when we form these ions, we'll observe that we pick up 1 more minus charge. And by picking up a minus, that means we've gained a valence electron. So if I take a look at a chlorine as a neutral element with its 17 protons and 17 electrons, its configuration comes out to be a neon noble gas core with a 3s2 3p5. But if we see a chloride ion, I still have my 17 protons, but I've gained an electron. And what this did is this had me pick up 1 valence electron. So now we'll see that the valence, or that the electron configuration, the electron configuration of most ions, we'll call these most main group ions, matches the electron configuration, the EC, of noble gases. So what this means for us is we see that we have our, that this one has an equal to argon configuration. We'll see the same thing. For example, if I have something like a magnesium as an element, I know that there are 12 protons and 12 electrons. So in this case, we'll see that we have a 1s2, 2s2, 2p6, 3s2 configuration. But in order for this to be like the closest noble gas, we're going to get rid of the 2 valence electrons on the end. And so we'll see that my magnesium with a 2 plus charge will still have its 12 protons, but only 10 electrons now. So this is a 1s2, 2s2, 2p6 configuration, which is equal to that of the closest noble gas, neon. So our goal with this, forming any ions and reacting with other elements, we form ions to resemble the electron configuration of a noble gas. And that's why we observe these charges that we do inside of the main groups. We'll talk in an upcoming video a little bit later about why, when we take a look at the transition metals, we'll see that the charges can vary inside the D and F blocks of our elements. But to help explain that, we're going to take a look at a couple then trends on the periodic table. And so when we take a look at these trends that come about as a result of the electron configuration, we're first going to look at the data for what we consider the atomic radii. So in this case, there are a couple important things to notice here. When I take a look at the atomic radius, it means that it's the or the distance between the nucleus and the outermost valence shell, or the outermost valence orbital. And so when we take a look at this, we'll observe that there's kind of a general trend here in the middle. So we kind of see that there's kind of like this oscillating, spiking trend, right? And at the peak of these trends, we'll see that the atomic number matches that for lithium, sodium, potassium, rubidium, cesium, and we kind of see that same idea about distancing between the principal energy levels, about how they kind of start to get closer together as we get farther away from the nucleus. So this makes a lot of sense, right? Because every time we jump up to a new energy level, the atomic radius is going to be the largest. So we can kind of make a quick summary that says, as we move top to bottom on the periodic table, we'll say that the atomic radius increases and that's because my valence electrons are in a new principal quantum level. So then let's take a look at a couple more general trends before we look at some of the specifics. So now you'll notice that as I move from like lithium to neon, sodium to argon, potassium to krypton, the general trend as I move left to right in the periodic table, we'll see that the general trend is that the atomic radius decreases And why do you think that happens? So let's think about this, right? So if I take a look at an atom of lithium, I have 3 protons and 1 valence electron. So why is it then when I take a look at, say, neon, that has 10 protons, that my valence electrons are significantly closer to my nucleus? And the answer is because it has to do with this number of protons. When we take a look at what we talked about, that shielding, our effective nuclear charge, or how much force the electron feels, we're going to see that this electron has an effective nuclear charge of +1 because these 2 core electrons cancel out 2 charges of the protons. Whereas when we take a look at our 8 valence electrons here, each valence electron in the second energy level has an effective nuclear charge of +8. Because 2 of those protons are canceled out by those 2 electrons, but all the other ones are fairly equal in the other energy levels. So we'll see that as we move left to right, the atomic radius decreases because the effective nuclear charge increases. So these are kind of the two general trends that we take a look at when we talk about atomic radius. Now you'll notice there are a couple exceptions as a result. So then let's take a look at some of these exceptions. For example, when we take a look at our second family here, we're going to zoom in a little bit. You'll notice that as we move across, this is lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon, right? Why is it that oxygen and fluorine have a larger radius than nitrogen? So let's take a look at that real quick. When we take a look at the electron configuration of oxygen versus the electron configuration of nitrogen, we'll see that we have a different setup. We'll see that nitrogen has a 1s2, 2s2, 2p3, whereas oxygen has a 1s2, 2s2, 2p4. So what this means then for us is that we'll start to see that there is a pairing of electrons in nitrogen versus oxygen. So what this means for us is that we'll see then our this pairing here in my 2p4, just to demonstrate this out, 1, 2, 3, 4 versus my 2p3, right? And so the reason that we observe this small jump in our atomic radius is because we now have one of the orbitals filled up, and there's electron-electron repulsions that are now occurring. And because of that repulsion, it just pushes the electrons a little bit farther away from the nucleus. And we'll see the same thing that occurs in fluorine until we hit neon, and we still see a little bit of an increase there relative to nitrogen. So because they're so close together in those p orbitals that are really close to the nucleus, we'll see that there's an exception here because of that. Now, there's some other interesting trends here within our period 4 and period 5 transition elements. So when we take a look at the periodic table, why is it that we observe an increase? Kind of moving along, let's zoom in here real fast just so you can see what I'm talking about. We've got calcium, right? Yeah, that's period 3. We've got calcium, scandium, titanium, vanadium, manganese, vanadium, chromium, there we go. Manganese, iron, cobalt, nickel, copper, and zinc, before we then jump into gallium. Why is it that we start to see this little bump here in manganese versus chromium, and same thing when we start taking a look at copper and zinc? Why do we observe these? Well, when we take a look at the electron configuration, we'll start to observe that, remember, for chromium, we have a configuration of our argon core, and we had a 4s1 3d5 because we don't have any pairings. But when we take a look at manganese, we'll still have that same argon core with a 4s2, 3d5. And so because of this, we'll see that my manganese now has that electron-electron repulsion. That starts to push out. And same thing, when I take a look at the difference between nickel, copper, and zinc, we'll see that we go from a configuration that ends with a 3d10 at nickel, but copper and zinc start to exhibit into the 4s1 that's a little bit further out. And so just because we're starting to fill up the 4s orbital and experience electron repulsion, we'll see that nickel is going to be a lot smaller than copper and zinc. And so when you take a look at these general trends, this is why we talked about some of the generalities, but this is why we see the trends in atomic radius when it comes to our transition elements. So just be aware, we've talked about some of the exceptions and why they exist, and oftentimes that's just due to some electron-electron repulsion. So lastly, I want to take a look in our final video here that's going to be coming up in just a few minutes about the ionization energy and some of the electron configurations of ions instead of just the electron configurations of our main elements. Stay tuned.